Good morning, my name is Yoshio Takaki Lomeli, and I am going to present my project called bismuth-doped titanium dioxide nanotube by anodization method. In this work, synthesis and characterization of bismuth-doped titanium dioxide nanotubes were studied. The first material to be used as implant were polymer. However, their mechanical properties are bad. On the other hand, metals have better mechanical property. The problem is that most metals don't have good biocompatibility due to corrosion wear and toxicity, but titanium and its alloys are among the most used metals as biomaterials due to their biocompatibility, osseointegration, mechanical property, and corrosion resistance. But their property as biomaterials can be further improved by applying an electrochemical method called anodization. We can pass to methodology section. The first step is the synthesis process. The synthesis was carried out by anodization technique using a graphite rod as anode and a commercial pure titanium substrate as cathode. The electrolyte was composed of ethylene glycol, water, and fluoric acid. For doping nanotubes, we added bismuth in different molarities like 0.5, 1, and 2 molar. For nanoscratch test, we were applying an initial load of 0.1 millinewtons that was progressively increased until reaching a final load of 500 millinewtons with a speed of 1 millimeters per minute, and 0.5 millimeters was the scratch length, and we use a conical tip of 120 micrometers of radium. To obtain the chemical composition, we use a XXX spectroscopy, and we use a monochrome source of aluminum at 250 watts and 12.5 kilovolts. In electrochemical process, we use ACE analysis, use a range of frequency from 1000 Hz to 0.01 Hz, and the potentiodynamic polarization test was taken in a potential range from minus 0.5 to 1.5 volts. So we can pass to result section. In figure 1, we can observe the diameter of nanotube without doping, and in figure 2, we can obtain the diagram of nanotube without doping that is near 500 nanometers. When we add bismuth as doping, we can observe that the quality of the surface increase and improve the morphology. So we can observe in figure 4 that the height of nanotubes increase and grow like 2 micrometers. When we go to nanoscratch test, we can observe that in high molarity of doping, we can obtain the less friction coefficient, and when we go to XPS spectrum, we can observe that the concentration of bismuth is obtained like 1.4% in the substrate that was doping with 2 molar bismuth, and the titanium obtained the 34% and oxygen 64%. And for this graph, we obtain the chemical composition, and we prove that bismuth is present in these doping nanotubes. So when we go to body diagram, we can observe that in higher molarity, we obtain better surface quality, as we can observe in same image, we can observe in body diagram. When we pass to Nyquist diagram, we can observe that the difference between the circle is not a lot, and we can differentiate this difference. When we arrive to Tafel plot, we can appreciate that undoped nanotubes indicate that the current start increasing at more novel potential. These curves indicate that undoped sample is more resistant to initialization and propagation of localized corrosion than doped nanotubes. And we realize we did some preliminary proofs of antibacterial tests, but we don't have enough results to reach a conclusion. For conclusion, the morphology of nanotubes was improved with increased the dopant. As can be seen in the image, the surface is better and the ground is high. In body diagram, we can observe the same, that the surface improve its quality. And in nanoscratch test, we can observe that the cathode friction decrease when increase the molarity. And we can observe that the nanotubes are doping correctly, because we can know in XPS test that the bismuth is present in nanotubes. That's all. Thanks for your attention.